So a bit of a roadmap. I'm going to start with, I'm trying to make this talk focus on the theme of being an observer. And so what I'm going to talk about is the broad notion. I think this first part of it at least is very close to what Seth said yesterday. I think his words were systems that gain information about the outside world. I'm going to put forward a proposition for how this notion of observer might be enriched if we add this ending clause that's in a certain sense teleological, that observers are systems that gain information about the outside world in order to stay out of thermal equilibrium. That if you are something that gains information about the outside world, you get high mutual information with it or something like that, but it is not germane to your staying out of thermal equilibrium, then you're not an observer. In a certain sense, for example, as I'll discuss, a hurricane is not an observer. Then, to be able to actually flesh this out, I'm going to do a very, very quick run through some of the, frankly, breakthroughs that have been occurring the past decade and a half or so. Susanna was alluding to some of them, Jim yesterday, in non-equilibrium statistical physics. They provide us the tools to be able to formalize this. This work more generally provides us the tools to go much, much further in, for example, analyzing the thermodynamics of computation than was possible 50 years ago, and so on. Rolf and Charlie were doing their pioneering work. The tools weren't around them. Now that we have them, there's actually some amazing things that are coming out of this community that we can exploit in analyzing other issues. And so then I'll bring the two together and give actually a formal definition of observers. What's very, very nice about this is that you can then look at a system and you can actually quantify what the observers are in it from outside. You don't have to start from that. The factor problem, so to speak, is given for you. Observers are not simply binary. It's not a matter of you are or not an observer. It's actually a real number. There can be multiple observers within a system. As the system evolves, the observers might actually dissipate or they might actually emerge, all kinds of rich structure that can arise. So I'm just trying to control my various limbs simultaneously here. So what is an observer? It's a system with some state space that acquires information about an external system. I think probably everybody can agree with that part of it. How do we quantify information? A nice little quote from one of the brilliant minds, of course, Claude Shannon. He himself pointed out that there are multiple concepts of information. In particular, two of them that he actually focused on, syntactic information, and that's his entropy and all of its relatives, the extension, Salas, Rényi, F divergences, things along these lines. There's also, though, a notion that Shannon himself discussed passingly, which is semantic information, not just the syntactic, but also what does the information mean. Traditionally, we in physics have focused on syntactic, but semantic information, what those actual bits mean, maybe, I'm just going to put this out there as a proposal, maybe at least as important if we want to actually formalize observation. And so the rest of this talk, I will be presenting a way to formalize semantic information to allow us to formalize observation. Okay, so an observer is a system, just repeating, that acquires information about an external world. It's common to define the semantic information of any such scenario by using some exogenously specified objective functions. People do this a lot, so this is going to be, for example, it could be a distortion function. If we're talking about the semantic information of a biological organism, it might be its fitness function in cooperative or non-cooperative game theory, utility function. The basic idea is that the information you get that some data you get, the amount of semantic information associated with it, is how much you can use it to increase your objective function. So for example, to a biological organism, some data, the amount of its semantic information is how much it can use that data to increase its fitness, to give an example. But for us, analyzing the foundations of observation and physics and so on, we don't want some exogenously specified objective function. We want any such objective function to emerge from within the physics of the system itself. So how might we do that? Well, one way to do it, and I won't by any means want to say it's the only way, is to say that observers, the ones that I know about at least, they are outside of thermodynamic equilibrium. So we sort of, in fact, I would say that if we want to discuss the notion of observer, at least outside of the context of a pure state. If we want to consider them, for example, in classical universes, then we are going to need to know something about non-equilibrium statistical physics. But in any case, if we just put out there as a proposal that for one kind of observer at least, say it's that way, they are outside of equilibrium, then you might say that a goal for such an observer is to keep being an observer. Which here what that means is that the objective function is to be far away from equilibrium. So the semantic information as far as observation is concerned, the observer has about his external world is high if and only if that information is necessary for it to stay away from thermal equilibrium. This is one possible way to define things. So to show this a little bit with some delightful PowerPoint, here's your external world, here is your putative observer, some data flow, some information flow going this way. And the notion is that the system is using that data to stay far from equilibrium. In other words, if this were interrupted, if there were this data channel, this information channel were interrupted, that the mutual information between x and y at this particular moment were set to 0, but then we evolved according to Hamiltonian physics after that, then because of this interruption in the data flow, the system would quickly relax to thermal equilibrium. If it had had that data, it would have been able to stay out of thermal equilibrium. Here's an example. You're looking up in the sky, and you notice that there's a meteorite descending on you. And based upon that, you can figure out whether you should appropriately jump to your left or jump to your right. So since you have made that observation, you get to stay far from equilibrium. You get to be alive, you're a living organism. If that data stream, the photons hitting your eye, if that were interrupted, you look up, you have no idea where the meteorite's coming. You might not even know there is a meteorite coming. And so in this case, there's a 50% chance of your, well, quite literally, going to thermal equilibrium. You might become quite literally toast. So this is an example, a toy example, a Gedanken experiment, if you will, of how if you successfully dodge a meteorite, then you are an observer according to these particular definitions. Let's return to that case of a hurricane. It's something that is exploiting, so to speak, a free energy flux from the hot ocean beneath it. That's how it stays hurricaning, how it keeps revolving. And so the ocean beneath the hurricane, that's its external world. X is the state of the hurricane. But if I were to actually just a single moment decouple some data from the ocean into the state of the hurricane, but then let the hurricane evolve according to its normal Hamiltonian, nothing will change. It's not somehow exploiting that information. It's not looking at the ocean to figure out, oh, if I go over there, let me change course, because I can actually stay out of equilibrium much better over here than, for example, if I continue at land and make landfall. Hurricanes don't do that. And so in this particular sense, a hurricane is not an observer. Okay, let's just take this and run with it. It passes the smell test as a way one might want to define observer. Using semantic information. So to be able to actually, so to speak, decorate these words with math, what we need is a broadly applicable definition of what it means to prevent an observation. And I'm going to invoke some ideas that, in a certain sense, their heritage goes back to Judah Pearl and his interventional causal information flow and things along those lines. But in addition to saying what we mean by interrupting an observation, we need some measure of how far a system is from thermal equilibrium. And this part is where I'm going to exploit some of these major advances in non-equilibrium statistical physics. So that was the first part, and now into this stuff that I keep singing the praises of, giving you a lightning review of a very, very small part of it. This is actually a kind of an amazing thing sociologically. There have been about at least 1,000 articles in the past decade, tons of PRLs, Natures, so on and so forth. A nice review, a review that I particularly like, is Parando et alia Nature Physics in 2015. There are many of them. And what they have uncovered, there are mentions of Crookes and Jarzynski, they fall into this world as well. They have figured out things like when you go down to nanoscale systems, on average, entropy increases, but you can actually quantify the probability of entropy going down. This is the kind of machinery we now have, fully formal physics. Everything is known. Most of it is actually canonical ensemble, though it has been extended to microcanonical, to unitary evolution. So even at that level of questions of was the early work on things like thermodynamics and computation, it's not even clear in that early work whether it was or was not canonical or microcanonical. We can now actually analyze it from both perspectives. It is starting to be extended into quantum mechanical formulations. And it tells us many, many things. For example, we now know that if I give you any time zero probability distribution over the states of a system and associated Hamiltonian, and then there's some other one at time 1, then we can actually go from this one to that one fully thermodynamically reversibly. The system is at thermal equilibrium throughout the trajectory in which you go from the one to the other. The most recent experimental test of this that I know of, just doing a Google search, was actually Nature Communications about a month and a half ago. There are some nuances to this particular study, but it's very, very well analyzed and understood from both theoretical and experimental basis. What this says is, in particular, this distribution can be going to that one. That can be a 2-to-1 map, like bit erasure. Logical irreversibility does not have anything to do with thermodynamic irreversibility. They are distinct concepts. That does not mean that KT log 2 is no longer part of the game, though. But it arises in a different way. So, for example, we can actually now, to calculate the minimal reversible work, that's actually what minimal work means. You're just invoking the second law here to establish that there's nothing that can be more efficient. The minimal reversible work to implement this map here, this transformation, in a special case where your Hamiltonian is uniform across everything, which is kind of what you're normally interested in when you're analyzing computation, it is actually equal to KT, and as Susanna emphasized, that's the temperature of the external heat bath, or canonical ensemble. This is the Shannon entropy drop from time 0 to time 1. Since you are out of equilibrium, the Shannon entropy differs from the thermodynamic entropy. And so if we now look at a special case, if we say our state space is binary, if the initial distribution is uniform, it doesn't have to be. But if it's uniform, if your ending distribution is a delta function, so what you're doing is actually bit erasure, well, since your ending distribution is a delta function, its Shannon entropy is 0. Since your initial distribution, we're looking at this specific case where it's uniform, you don't know if that bit were up or down, then its initial Shannon entropy was log 2, so there's KT log 2. This is reversible work, thermodynamically reversible. Like all thermodynamically reversible processes, like a Carnot engine, for example, it involves semi-static or quasi-static, if you prefer, transformations, and therefore, strictly speaking, takes an infinite amount of time. But that's true of all classical thermodynamics as well. Okay, but this is talking about what you can do reversibly. It turns out you can also do all the analysis for the irreversible contribution. So the dissipated work, you do work on a system, in general, part of it will be reversible, you can get it back. But in the real world, when you're doing things finite time, part of it you will not be able to get back. You will have caused turbulence, et cetera, et cetera. This is the exact expression for the rate at which work is dissipated when you are undergoing, in this case, it's a master equation process. R is the transition rate matrix, and P is the current distribution. This is, for example, this particular formula is directly out of Esposito-Van den Broek, a nice review paper. We can now quantify these kinds of things. We can disentangle what part of the, given any master equation for a process, we can write down what part of what's going on is reversible change in entropy and what part is irreversible. Here, everything that I've said so far, this is actually just stuff that's been known. Many others did it. Many, many others have done it over the past 10 years or so. Here is one small contribution that me and Artemi have made that's relevant to what I'm presenting today. Let me fix a system. So I'm fixing a process, fixing a master equation. And suppose that there is some particular initial distribution that results in the minimal amount of dissipated work. If you change that initial distribution to be something other than this one that minimizes dissipation, you are now going to, in general, dissipate more work, given by this drop in the KL divergences. By the chain rule for KL divergence, this is non-negative. In a certain sense, this is a new kind of a second law. It's an equality, not an inequality, and it's saying how much extra work gets dissipated due to changes in the initial distribution to the system, not due to changes in the actual dynamics of the system. So these are just some of the kinds of things that fall out of this work that all these other people have been doing. Now let me show, bring it all together, how to take all of this stuff, which hopefully I've sufficiently browbeat everybody, so they'll just accept what I'm saying about that, and use that to actually formalize this way of saying what an observer might be. So recall we're saying that here's your external world, 10 minutes, okay, great, I'm going to be done early. Here's your external world, here's you, there's some data right here, maybe, maybe not, but whatever. There's some, your mutual information is non-zero at that time, and the whole notion is that you are an observer if you stay far away from equilibrium with that data, but if I just interrupt that, then you relax quickly to equilibrium. We need to be able to define those two things. How do you chop him off, and then a measure of how far you are from equilibrium. So the notion of how you present observation is, well, the most obvious thing to do, which is always a good place to start, is to simply say, well, you've got some joint distribution at that time. Let's just replace it with the product of the marginals, and then we just evolve according to the Hamiltonian as we did before to get the future evolution of the system. So it's going to be coupled again right after time t. We're just, in essence, we're starting an initial condition to the subsequent evolution where you are independent, statistically independence holds between you and the system you're observing. So that part's actually quite simple. It's related to Pearl's things because you're actually intervening in the stochastic process. And now, let's look at some possible measures of disequilibrium, of how far you are from equilibrium at some future time. There are tons of them. Two of them that are suggested by non-equilibrium statistical physics are these. The first one is the difference of the Shannon entropy of the initial state of the system, of the state of the system if there's no prevention of the data observation, minus what the Shannon entropy would be if you did actually interrupt that data flow, because from this work of all these other people, we know that that is the maximal amount of work that you could actually extract thermodynamically reversibly from going from that relaxed state to this state. So that's one way of measuring how far you are from equilibrium at this particular time. Another measure that's suggested by this analysis that these other people have done is the rate at which irreversible entropy is being produced, the rate at which you are dissipating work at this time. When you're at thermal equilibrium, this beast is zero. You're just Boltzmann distribution, ain't nothing changing, you're not dissipating work. But if you're far away from equilibrium and you're staying that way, actually you have no choice, you're going to be dissipating work. So these are just two possible measures that one could apply to actually give a completely broadly applicable formal way of taking any particular system and associate Hamiltonian and defining essentially thermodynamically whether it is an observer or not. So to recap that, you prevent the observation, that interventional operator, which in one case you do it, in one case you don't, is just replacing a joint with its product of marginals. There are at least two, and possibly many more, measures of the disequilibrium that are suggested by modern non-equilibrium statistical physics. There are a bunch of advantages to this particular perspective on what observation is. One of them is that if we use this disequilibrium measure as a quantification of being an observer, we now have a real valued degree. I can give you a system, be it a hurricane, be it a paramecium, be it a human being without enough coffee, whatever you want. I can give you that particular system and assign a real number. To what degree is it an observer? It's not just a bit. It's like these vacuous questions about is the system alive or not. Well, if you're going to have any kind of a rich way of analyzing these kinds of concepts, you don't want to just be looking at a bit. You want spectrums. And that's one thing that this gives you. Moreover, a given system can actually have multiple subsystems within it that are observing other subsystems. Again, you get a much richer structure. If I give you the evolving system, if I give you some Hamiltonian and some initial joint distribution, you can then actually sit down and solve for what are the subsystems, potentially more than one, that are observing which other subsystems, and to what degree do they do so. If I then have this same thing, the Hamiltonian and the joint initial distribution evolving in time, then in general, one would expect that you are going to have emergence of some observers. There weren't any initially, but then you start to get some because this real valued disequilibrium measure for some subsystems got to be quite high concerning other subsystems. It might be your observer goes away. I expect that's going to be happening with this observer within some number of decades from now, for example. But then I think Susanna's got a baby here, so that observer is basically coming online. It's emerging. You can talk about observers merging. You can talk about them fissioning. In general, one would expect actually a very, very rich graphical structure relating observers and observees over time. And one thing that would be quite fascinating, for example, is to map that against things like food webs in ecosystems or systems of this nature, and actually look at broader scale systems, say social systems, what have you, and see which parts of them can be viewed as observing what other parts of them, and how much that particular kind of a relationship matches up with the other kinds of relationships that we think about when we view things like the environment around us, the ecosystems, the socio-political systems, what have you. So anyway, concluding, bringing it all together, observers, if we are away from the quantum mechanical world and we're talking about, or to put it another way, if we're not in a pure state, classically you might think that observers are non-equilibrium systems. Certainly I think we all agree that they are systems that acquire information about the external world. One way of quantifying information is semantic information, and when you take that and some of these recent breakthroughs in non-equilibrium statistical physics, we can actually formalize the notion that the observers are systems that are non-equilibrium, acquire information, and if they did not acquire that information, they would quickly relax the equilibrium. That's what the difference between something that's just getting free energy from the environment and something that's actually observing the environment. We can then look at some simple real-world toy examples, and they pass the smell test. Do we want to actually say this is an observer? And then this notion of observers got all these other advantages. There are many others as well that I've not gone into today, but it provides a real valued measure. It's not just a bit. You can solve for what subsystems are evolving, are observing other ones. As I mentioned, some of this work in non-equilibrium statistical physics, some of it's being applied now in quantum mechanical scenarios, and there is already some work with microcanonical, where it's mostly, I think, in a classical context. And so it would be very, very interesting to see if you can actually join those up and somehow say anything at all insightful about the question of if you've got a pure state quantum mechanically, what are the observers in it, things along those lines. I should also mention, connecting up with some of the other issues of interest in this conference, those thousands of papers, to my knowledge, Jim or Susanna or somebody correct me if I'm wrong, but to my knowledge, there's nothing in there, in the purely classical parts of it even, that considers doing any of these analyses of non-equilibrium statistical physics in co-varying Lorentz frames. Never mind anything that's tried to introduce Einstein's equations and make it be general relativistic. None of that has been done. It's all sitting there to be done. Might there be something interesting, for example? Remember I was saying that the fluctuation theorems of people like Jarzynski and Crookes and so on, they say that when you get down to nanoscale systems, that yes, under expectation, entropy goes up, but here is the very substantial probability that it will go down. What happens to those fluctuation systems if we could actually apply them, for example, near the event horizon of a black hole? Would any of this have any relation to things like Hawking radiation and so on? I have no clue. It's all out there, though, work to be done. There's tons and tons of things in all these branches of physics, as well as biology and computer science, that we can start using these tools from non-equilibrium statistical physics to analyze that nobody's actually gone after before. And I've just stumbled across some ways of applying it to things like observers and some other work for computation. But my God, there's just so much out to be done there. And I'll just sort of end it with that kind of a plug that people go out and learn that literature. It's very, very rich. So I'll end it there.